thank you very much. Thanks for coming, everyone. So for the uninitiative, I thought I'd just give you an idea of some examples of what the Grothendieck-Witt group of various fields look like. The idea being we're going to be defining Euler characteristics, which are classically integers, so quadratic versions, and they'll land in the Grothendieck-Witt group instead of the integers. And so just to give you an idea of what extra information you're getting. Okay, so first, simple case, if f happens to be algebraically closed, or even if every element in f is a square, then of course, then the Grothendieck-Witt group of f by the rank homomorphism is isomorphic to the integers, and this just follows because every quadratic form is diagonalizable. So we're always working in characteristic not equal to 2. Right? So if you can always, by just change of coordinates by the square root of the coefficient, change this to the sum of squares, so they're all the same. So it's just the number of, I equals 1 to the rank. Okay. Good. So that's the simplest case. So in that case, our invariant isn't giving anything new. The rank homomorphism is what gives back the old invariant from the new one. Okay, so what about f equals r? Then, in addition to the rank homomorphism, we have the signature homomorphism. So over r, if you diagonalize your form, you can write it as a sum of squares plus, so 1 to a, and then from a sum 1 to b of minus squares. All right? And then the signature is just a minus b. And it's easy to see that that's a ring homomorphism. And if you take so now we have two maps to z, so we can map into the product, rank and signature, and that's in fact an injection. And what's the image? The image is just the obvious condition that the rank and the signature are congruent mod 2. Okay, if you think about it a second, you'll see that that has to be the case. Okay, so now let's look at a general field. And, well, the first thing to look at is the kernel of the rank homomorphism. That's the augmentation ideal. And, well, you have another homomorphism here, the discriminant, going to the units in the field mod squares. And so if we take our quadratic form and we represent it by a symmetric matrix, then the discriminant of Q is just equal to the determinant of this matrix. And since change of variables on a quadratic form change by A and A transpose, it just changes the determinant by a square, so you get a well-defined invariant here. And in fact, this discriminant gives you tells you exactly what this ideal modulo its square is. Okay, maybe with that in mind, let's look at the case f is a finite field, q equals p to the n, p an odd prime. Then, well, then you have q goes to the integers, and you have if, and it turns out that the square is 0, so this is just isomorphic to fq mod fq squared, which is, well, of course, it's just z mod 2, because we know that the unit group in the finite field is cyclic. Okay, and then this extension splits if, well, let's say, at least for q equals p, congruent to 1 mod 4, and for Q equals P doesn't.
What do you mean by it's the right-hand side is the free abelian group?
Yeah, well, it's a ring homomorphism. What I mean is splits. What I mean is that this thing is the group ring on the units mod squares. And it's not. So it's not, that's what I mean by splits. And it's not if P is tangent to 3 mod. Maybe couple more examples. What about p-adic fields? Finite extension. And again, let's take P odd. Just to make P equals 2 is, of course, the oddest prime, so we avoid that. So then, well, we know what I mod I squared is. And this is isomorphic to Z2 cross Z2. And then what about I squared mod I cubed? Well, this is in fact true for an arbitrary field. This is isomorphic to K2 Milner. This is for all F. Characteristic not 2, mod 2. And sort of a Hilbert symbol map. And in this case, you have the Hilbert symbol AB, let's say F, well, you have the symbol ABF, which is equal to +1 if the equation x squared over A plus y squared over B equals Z squared has a non-zero solution, -1 if it doesn't have a solution. And this symbol tells you, in the p-adic case, what's going on here. So, yeah, I won't write down the exact. So you have the so-called Hausdorff-Witt invariant, which takes a quadratic form and sends it to the product of these symbols. And this tells you the class here for the p-adic field. And then finally for Q, I'll just say that let's look at the Witt group. I mean, the point is that the augmentation ideal for the Witt group mapping to rank modulo 2 is the same as the augmentation ideal for the Grothendieck-Witt group, and it's sometimes more convenient to write it this way. So this thing injects into, you have the Witt group of R, and then you have the product of the Witt groups for all the p-adic fields. So,
in the p-adic case, does this filtration
oh yeah, good point. And yeah, in general, for the p-adic field, the point special here is that I cubed is 0. Yeah, thank you. In general, it's not, but right, that's exactly the point. So, yeah, so essentially it says if you know the signature and you know these, the discriminant, and you know all the Hausdorff-Witt invariants at each prime, then you know the quadratic form. So that's the theorem, that a quadratic form over Q is determined by its rank, its signature, its discriminant, and the Hausdorff-Witt invariant. Okay, so, and one other thing to note, the rank and the signature are integral invariants, and all the other ones are mod 2 invariants. So there's this two torsion is the important part, except for the rank, which is essentially what we already know about, and then the new invariant is the signature. Okay, good. So I hope that gives you some feeling for the type of invariant. So it is sort of an arithmetic improvement on just the integral information given by the rank. Okay, so let's look at Euler characteristics. So there's the basis. We have the classical Euler characteristic of a topological space. So for that, we need some finiteness condition. So let's let X be a finite, say CW complex or finite simplicial complex. Doesn't really matter. Complex, compact manifold, anything of that homotopy type. Then we have the Euler characteristic. I'll decorate it with this top. And this, there are various definitions. Let's just can take the sum of the ranks of the integral homology. Okay, and it's a finite sum because of the finiteness of the complex, and the ranks are all finite for the same reason. Okay, so that's one way. Now, if X happens to be a compact manifold, we can get at this thing through other characteristic classes, namely through the Euler class of the tangent bundle. So we have the tangent bundle, and there's you don't really need to assume that the X is oriented. So we have a local system. Let's call OR X the orientation local system. So at each point in the manifold, you have two choices of orientation. You take sort of the integers based on all multiples of orientations. And as you move around in the manifold, it gives you a family of copies of the integers, which, say on the Mobius band, if you go around, they would come back to the by minus. So formally, if X, let's say, has dimension of X is D, then what you look at is at a point X, you send it to the, one way to say it is the Dth cohomology on X with supports at the point. So this is isomorphic to Z, but there are two choices of the isomorphism, and that either gives you a constant local system, which is the oriented case, or the non-constant one, which is the unoriented case. Good. In any case, I'm not going to define this, but there's an Euler class. It's a characteristic class of a bundle, and it's the Euler class of the tangent bundle, happens to live in the Dth cohomology of X with coefficients in this orientation local system. And since X is compact, you also have a push-forward map or a degree map or a trace map, various ways to say it, to H0 of a point with Z coefficients, and that's just Z. And so this Euler class goes to an element here. Let's just call it pi x lower star of the Euler class of the tangent bundle. So degree-oriented degree of the Euler class. And well, I'm going to call this the Gauss-Bonnet theorem. Maybe that's a little exaggerated, but some form or other of Gauss-Bonnet that you can calculate the Euler characteristic through characteristic classes. It just says that the topological for X, a compact manifold, this degree of the Euler class of the tangent bundle is just equal to the Euler characteristic. Okay, good. So I want to give a sort of fancier categorical interpretation of the topological Euler class as follows. So, right, so I wrote down ranks of the homology. The homology is calculated by the singular or simplicial or cellular chain complex, whichever one you like, it doesn't matter. Let's just call that C star of X, the integral chain complex for X. And this is a since X is, this is a complex, essentially, you can represent this as a finite complex of free abelian groups of finite rank, and determines an element in the derived category of abelian groups. All right, this is just a category of all complexes of abelian groups where I invert all maps which are isomorphisms on homology. Okay, and it turns out this thing has a tensor product of complexes that actually gives you a well-defined symmetric monoidal structure here. So this is what's called a tensor triangulated category. And for us, so tensor just means you have a symmetric monoidal structure. You can multiply things, and you have a symmetry isomorphism. You have a unit. The unit, of course, is just the integer is viewed as a complex in degree 0. Okay? That's the unit for the monoidal structure. And it turns out that because of the finiteness condition on X, that this object, Cx, is what's called a dualizable object. In the derived category. So this doesn't refer to the triangulated structure, it's just about the multiplication. And so what does that mean? Well, there are various ways to say it. Let me say it in a sort of concrete version. It says you have, it says that it implies, anyways, you have two distinguished maps. So first of all, there exists a dual, and so it's just another object in this category. And there are two maps, one to this tensor, the product, and another one from the tensor product written in the other order, called evaluation. So just to give you an idea of what these are supposed to be, and then there's two relations that they have to satisfy, which I'm not going to write down. But think of the case of, instead of the derived category of abelian groups, maybe that's a scary category, think of the category of finite dimensional vector spaces over a field, with the usual tensor product of vector spaces, and the dual is the dual vector space. And what's this map? If it's a finite dimensional vector space, it's dualizable, and this map sends 1, which is just the field, sends 1 in the field to the identity map. Yeah?
It's related to the cochain complex, the dual.
Probably that's what it is, but yeah. But back to vector spaces, this you view as the endomorphisms of the vector space, and you send 1 to the identity. So if you choose a basis for the vector space and a dual basis, it sends 1 to the sum of the EI duals, tensor EI duals. That's the sort of delta. And this one is evaluation. Well, if you have an element in the dual and an element in the vector space, you can evaluate. Okay, and then there's a map here. Remember, it's a symmetric monoidal category. So you have the symmetry isomorphism, which switches the factors. And note, in the triangulated setting, this has a plus minus depending on whether the 2 degrees you're switching are even, or one of them's even, or both of them are odd, right? The usual story. So that's why you get this minus sign, and you can then define the following. This composition has a name. It's the trace of the identity map on here. So you get a trace of the identity map, and this lives in the endomorphisms in this category of this unit object. Okay? So I just gave you a general description in a symmetric monoidal category of essentially two, not quite what a dualizable object is, but at least 3 things that a dualizable object gives you. It gives you a dual object and 2 maps. And then once you have that, you can define this trace of the identity as an endomorphism of the unit object.
And sorry, what is
Yeah.
tensor product on the derived degree?
Yeah, it's whatever. It's on complexes of free Z modules, you just take the tensor product of the complexes. And then you write any complex as quasi-isomorphic to such a thing. And that... We what? Question? Was there a question? Somebody said something. Yes. Really? Yes, really.
Really?
Really? Yes, really.
Have such kind of. I mean, is every complex as a positive morphic as the degree complex? Even not talking about.
Yeah. Maybe. Flat. You can assume that they're flat, yeah. And if you have a complex of flat modules, then that's how you take the tensor problem. You can choose. You can take the cellular chain complex, the simplicial chain complex, or the singular chain complex. It's one of this is the integral chain complex for X. Okay. Good. So, and where does this trace of the identity live? That it lives in the endomorphisms of the unit object. And this is just, well, Hom of the complex Z in degree 0 to itself. And this is just H0 of this complex, which is just Z. And so you get an integer, and what integer is it? Well, it's equal to the Euler characteristic of X. And the minuses, how do you tell that? Well, you just have to see sort of what happens for the free Z module in concentrated in degree I, and you see when I is odd, the switch thing introduces a minus sign, and when I is even, it doesn't. Okay, it's easy to check. Okay, good. So we have this categorical definition, and once we have that, we can try and use some categories to try and refine this. So one could try to refine this topological Euler characteristic, viewed this way as the trace of identity, by refining this category. So, for example, to the stable homotopy category. So this is the homotopy category of spectra. So we've mentioned what spectra are. It's a series of spaces together with bonding maps from the suspension of the nth one to the n plus first one. And this also is a symmetric monoidal, in fact, triangulated, although category. And you have, for your object X, you can associate, instead of the chain complex, you can associate the suspension spectrum in here. So this is the object where the nth term is the nth suspension of X, and the bonding maps are just identities. Okay, it's some object. And there's actually a map back to here, which essentially sends the symmetric monoidal map, and it sends this to its chain complex. Let me not say too much about that. And it's a symmetric monoidal map, so you can take the trace of the identity of this guy here. It turns out this is dualizable. This will still be dualizable. And so you can take the trace of the identity on this guy in SH. This lives in the endomorphisms of the unit in SH. And what's the unit? The unit is the sphere spectrum. And the endomorphisms, instead of H naught, it gives you pi naught of the sphere spectrum. Let me call this S. And this is just the stable, well, it's just the stable pi naught of spheres. This is the limit pi n of Sn, but pi n of Sn is just the integers and stable under suspension, so this is just the integers. And since pi n of Sn is just Hn of Sn, this is the same invariant we had before, so nothing new. Oh well. Nothing. So I can't make a crying emoji on the board, but if I could, I would. All right, but we're not done yet. So I barely mentioned last time the motivic stable homotopy category. So let me take this opportunity to say a little bit more about it. So we can, of course, the X is a topological space, we're kind of stuck there. But now we're really interested in X to be smooth, and that means finite type separated variety, so scheme over some field K. And then we look in, or even, we look in the motivic stable homotopy category over K. Okay, so let me give a somewhat more general discussion of what this thing is, or maybe not what it is, but a little bit about it. So so this is a brief digression on this stuff. So let's fix some B, a reasonable, so Noetherian, finite dimensional, whatever, base scheme. Fixed base scheme. And then we have K, finite type, smooth, separated B schemes. And then this sits inside here, where this is just finite type. Separated, if you like. Okay. And then, good. So we have the notion of motivic spaces over B, let's say pointed. Just go right to the pointed ones. So I was a little vague about, so space would be just CW complex, or probably a simplicial set is the best model for spaces, and then spaces, pointed spaces over B, are just functors or presheaves on smooth varieties over B with values in pointed spaces. So take your favorite good model for pointed spaces. Pointed simplicial sets are maybe the best one for me, and that's what a motivic space is. So what that means is you just associate for every Y smooth variety, you associate it some space, X of Y, a pointed space, and this is functorial in Y. So if you have a map, F from Y to Y prime, then you have a map in the other direction compatible with composition. Good, that's a motivic space. And just as spectra are, maybe I should say that anything you can do in, say, pointed spaces, you can then do in presheaves of pointed spaces just by doing that operation at every value of your presheaf. So if you have two pointed spaces, you can take their pointed union, or you can take their smash product. You can take limits, you can take colimits, just do the limit or the colimit at every value of your presheaf, and that gives you the limit or colimit in the presheaf category. So it's a very flexible construction. You also have sort of two special kinds of spaces over B. You could just take a space in the usual sense and take the presheaf that has that space as its value all the time, and all the maps between them are identity maps. So you get a map. This thing sits inside of spaces over B by just taking constants. And then you could also take any presheaf of sets on smooth varieties over B gives you a presheaf of spaces just as a discrete space. So in particular, if you have a smooth variety, you have the representable presheaf, which is just for X. If you take a smooth variety X, you have the Pre-sheaf, its value on y is the maps of y into x. So these are the representable ones. Well, of course, you have to plus a base point. So you add, at each one of those, you just add a separate, new base, a base point. Okay. Good. So you have, and then you form P1 spectra in spaces, pointed spaces over B. So an object here is just a collection of pointed spaces plus maps from the suspension. So we can take En, we can take its P1 suspension. This makes sense. We take P1 as pointed by infinity, mapping to En plus 1. So I'll write P1 for just the scheme P1 over B pointed by infinity. Okay, good. So that's it's not exact, it's not this thing, it's a slightly different that. I use a base point, not a disjoint base point. Good, whatever that is. And then you form this guy here is gotten by localizing this guy. So with respect to, so I guess three things, I'm just going to say it vaguely. So with respect to the Misnevich topology, on this category, with respect to A1 invariance. So if you have a space, you want this thing to give you an isomorphism, and then you want it with respect to P1 stability. So, right, you just take stable homotopy groups instead of homotopy groups. Good. That's more or less what this is. And I should just say that there's a functor, this representable functor business here gives you a functor, let's say MB, from smooth varieties over B to this category. It just sends some x B to this infinite P1 suspension spectrum of x, which is x with an added base point, x smash P1, x smash P1, smash P1, etc. So you have a functor, and then you can define, so this is the missing part from last time, you can define the bi-graded. Oh, I should mention that on this category, you have this operation of suspension with respect to P1. This is an auto equivalence. It's essentially why you took spectra. It's more or less built to make the suspension operation an auto equivalence. And so, in other words, this is the operation smash with P1. And this thing is also canonically isomorphic to a composition of smashing with the constant pre-sheaf S1 composed with smashing with the GM. So this GM is usual. It's the affine line minus 0 pointed by 1. That's because there's an unstable version of this, and in the homotopy category of pointed spaces, P1 is isomorphic to S1 smash GM. It's because, yes. Okay, so, and since this is invertible, each of these are also invertible. So you have lots of invertible guys on there, and then you can define for E an object in here. It gives you a cohomology theory. You can define E, A, B of some x by just you take the Homs of this motive of x into, so you take this is this guy here. This is just a convention, by A minus B and B. Well, it's a convention. Take the maps here. And you also have these homotopy sheaves, so I'm going to use the other convention. This is equal to the sheaf, Misnevich sheaf, on smooth varieties over B, associated to the pre-sheaf So if you have some U, smooth variety over B, you can take the maps, and now you, since it's supposed to be homotopy, you put the suspension on the other side, and I change my indexing convention by doing this. So it's not exactly coherent or consistent with what I did before, but that's what it is. Okay, good. So, now I can just remind you, just to finish up from last time, the things that were right at the end. And so I can remind you now, before we go into Euler characteristics, okay, any questions about this stuff? That was a whole big package at once. Let me ask for questions. Yeah.
So you did quantum spaces to be big enough to contain S1, GM,
Well, you mean that's why you use pointed spaces, or what's your question?
Pointed spaces is what pointed CW complex is?
No, this pointed spaces over B are.
No, just the categories SPC.
Yeah, I mean, so I was vague about what model. So if you want to fix it, you can use simplicial sets.
Okay. But you should take something that's general.
Yeah. Should be a model category. Version of topological spaces. So, and if I don't want to get into trouble, I would just say use pointed simplicial sets. Okay, so then in this regard, so we have the usual yoga. Okay, there's a whole big machinery for defining the smash product of spectra, and whichever machine you want to use, it more or less works here. So this becomes, with smash product of spectra, this is a symmetric monoidal triangulated category. The shift functor is this S1 suspension, not the P1 suspension. Just a remark. And the unit one is this motive of B. So it's also written as the sphere spectrum over B. Just the suspension spectrum on the base scheme. Okay, and then now for B equals K, a perfect field, then we have, and maybe again, always working away from 2, then last time I mentioned the theorem of Morel. So let me just say in advance, I define these for a given X smooth variety over my field. I define these sheaves in the Zariski topology on X, these Milner-Hurwicz sheaves. And let me just say that this extends to be a Nisnevich sheaf on the whole category. So you have functorial pullback maps for any maps of smooth varieties. And it's actually already a sheaf in the Nisnevich topology. So that's what I mean by this sheaf. There is a canonical isomorphism of Nisnevich sheaves on smooth varieties over K, pi 0 and skn, isomorphic with Milner-Hurwicz minus n. That's sheaf. Okay? And what that has is the corollary. You evaluate this at K and take n equals to 0. It says that the endomorphisms of this unit object here, remember we're looking, that's what our trace of the identity is going to land in here. This is equal to pi naught of sk naught evaluated at K, and this is just Milner-Hurwicz 0 of K, which by Morel's other theorem is just the Grothendieck-Witt group of K. Okay, so I hope, I stated this last time, and I hope this discussion makes this a little more clear. Okay, so now back to Euler characteristics. That's the end of the digression. Okay, so it turns out, so let's work over, well, yeah. Do I want to work over a field? Yeah. Let's take now B equals spec of our field. And the thing to note is, so this is not a not completely trivial construction, but goes back to Vojevodsky, improved by Ho Hu and Joel Ryu and many others. But when you take this suspension spectrum of, so for X smooth and projective over K, this thing in here is dualizable. And you can improve this. The category of dualizable gadgets is closed, has a 2 out of 3 property with respect to distinguished triangles. And so if you do that, you can extend this. In fact, this implies that this motive is dualizable if there exists an open immersion X inside of some X bar, where now this guy is smooth and projective over K, such that the complement divisor D, well, D is assumed to be a divisor, is a simple normal crossing divisor. So in the case of a surface, it means it looks like this. So this is your X, and this is your X bar, and this is your D. Okay, locally looks like a union of coordinate hyperplanes in local étale topology. Good. So this says, for example, if K has characteristic 0, so admits resolution of singularities, it says all X smooth over K have this motive, this suspension spectrum dualizable. Yeah, so now we're in business. In whatever setting, we take one of these good X's, it certainly includes all the smooth projective X over K, and we can then get an Euler characteristic defined as the trace of the identity if you have resolution of singularities. Yeah. So, and if K has characteristic 0, you do have resolution of singularities. And I guess there's a recent article by Hironaka saying that that's true over any perfect field, but let's leave that for others to worry about. Pardon me?
In the topological case,
Yeah.
the stuff of X is always dualizable. Is it
Yeah. So the method of constructing the dual is based on the method that you can use to construct the dual in the stable homotopy category of a finite CW complex. Right, Spanier-Alexander duality or something, right? You try and there you embed your thing into a sphere and you take the complement and you try and do something like that here. It's a little more difficult because there aren't enough spheres, but you can still do it. I'll say a little bit about it a little later, some aspects of this construction, but it's a little complicated, so I don't want to get into details.
Does the theory simplify at all if you assume you can make it close?
Which theory?
What you're about to do?
Well, it simplifies to the point of being useless. because then you just get back the old Euler characteristic. Yeah. Yeah. Let's have any other trivial remarks before I proceed?
Of course, I don't have Morel theorem in this case. But if I try to repeat this argument using VM instead of SH, do I just get Z?
Yeah, right. And then, so, right. Because the endomorphisms of the unit object in DM is just the integers. And then you can compare with, say, taking a Betty realization or an étal realization, and you see you get your favorite definition of the usual Euler characteristic. You know, you pass the algebraic closure, and the integers goes to the integers by the identity, right? Or it goes by an inclusion integers into QL. If you're in the L-adic setting, it's an inclusion. And so, yeah, you get the usual, yeah. So I'll make another trivial remark about that when the time comes. But now that we've got that out of the way, yeah, let's see. Okay, so thus we have the following for such x. We have this, let's call it the Euler characteristic in SH of k of x, which by definition is this trace of the identity on this suspension spectrum of x in SH of k. And this lives in the endomorphisms of the unit object, which is the sphere spectrum. And by Morel's theorem, this is just the Grothendieck-Witt group of K. So, I should just mention, so we're going to see that in a second, but Federico's comment was, this trace of the identity is an invariant, or it's functorial with respect to symmetric monoidal functors. So anytime you have a symmetric monoidal functor from SH of K to any symmetric monoidal category, it'll send this Euler characteristic to that Euler characteristic. And so what that says essentially is when you take the rank, I'll just say it this way, when you take the rank to the integers, this thing will go to some, I'll put topological Euler characteristic of X, which you, as I mentioned, you can compute this in various ways. You can compute this by taking the alternating sum of L-adic cohomology groups of X over the algebraic closure of K. That's one definition. Take the ranks of the L-adic cohomology, and that will give you the same, but as a comparison theorem, if X happens to be over a field of characteristic 0, you get the same thing by taking the C points of X and taking its Euler characteristic as a topological space. So this is equal to just X top of XC for K inside of C. So the rank is giving you this thing that we had before. Yeah, was there a question?
For non-projective scheme, do we have a correct?
Yeah, if you're in characteristic 0, this works for any smooth scheme.
The cohomology of the OX is not 5-dimensional.
Sure it is.
They're not taking the cohomology of OX.
You
They're
take
taking étal cohomology or
singular cohomology.
singular cohomology.
Yeah, any quasi-projective variety has homotopy type of a finite CW complex. Okay, so good. So harking back to the old Gauss-Bonnet theorem using Euler characteristics, let's look at the other way of doing this. So here's another possible construction. This will use our sheaves, Milner-Hurwicz sheaves. Okay. So we talked last time, we introduced these Milner-Hurwicz sheaves, so with a twisted line bundle, and they mapped onto these Milner sheaves. And then we had these Chow-Witt groups mapping to the usual Chow groups. And these things we said were just gotten by taking the Hn on X of these Milner-Hurwicz sheaves twisted by L. And this thing by Bloch's formula is just Hn of x Milner n. And so this map here induces this comparison map here. And these guys have certain functorialities. So I already mentioned that the Milner-Hurwicz sheaves extend to be sheaves on the smooth varieties for the Nisnevich topology, and it's the same for the Milner sheaves. So that says you have for f from y to x a map of smooth varieties. You have an associated map f star, on the, let's say, from Chow n of x L to Chow-Witt of y, coefficients at f star of L. Yeah.
Now you are assuming K is perfect.
Sure. I mean, I think for this you don't need to assume it's perfect, but let's assume it's perfect. Why not? I'm a reasonable man. I don't care. Okay, and now for f, let's look at the other functoriality. So for this proper, let's say relative dimension d, you have a push-forward map. In fact, on all this of course is just a special case of taking the cohomology degree equal to the Milner-Hurwicz degree, and it works for all pairs of integers, but I'm just not going to write it down. You have a push-forward map, and this is where it gets amusing. That's why we needed this. Another reason why we needed this L, it goes from Chow n of y, and your L is on x always, and you can take f star of L, but now you have to twist by a relative dualizing sheaf. I'll say what this is in a second. Oh, yeah. Sorry. Yeah, and this is why I have to make a lot of corrections here. So y over x, yes, and this is the Milner-Hurwicz Kn sheaf. There we go. That looks better. Going to Chow. I hope it's better.
What's the K in Milner-Hurwicz is not needed.
Oh, yeah. I guess I don't need it, right? Yeah. Okay, we'll eventually get this right. There we go. Okay. Chow n minus d of x L. So what's this omega y over x? This is just, okay, if you know what, okay, so y is smooth. So you have this thing, these are the Kähler differentials over k, and then omega y over x is equal to the top exterior power, and omega y, that's omega y over k, is just equal to omega y over k tensor f star of omega x over k inverse. Okay, these are all just line bundles. And the idea here is, one way to see how to do this is, remember we had, I'll just say it, we had this resolution of the Milner-Hurwicz sheaves in terms of Milner-Hurwicz sheaves of residue fields of points of various codimension. And so you think of it as like cycles with various funny coefficients. And for example, at the stage when we're looking at these Chow groups, remember the coefficients of the cycles were some kind of Grothendieck-Witt group, perhaps twisted by some line bundle. And now if you have a proper map, you can map cycles on y, like the image of a subvariety of y is a subvariety of x, and the codimension gets lowered by the relative dimension of the map. And then there's a map, then gives you let's say a finite map from a cycle from a subvariety of y to a subvariety of x, and there's a transfer map on Grothendieck-Witt groups called the Charlow transfer. So what it does to the unit for a finite field extension, you have the trace form. Let's say if it's a separable extension, then it's just given by essentially the trace form of the finite field extension. So when you put that all together, you have to, of course, generalize that to take care of the other groups that are involved, but that's roughly how you define this. Yeah.
He says that even if you add this trivium, you can't define push forward without distinct.
What do you mean? That's the definition. I didn't define it, but that's what it is. That's what it looks like. What do you mean? You can define it. That's what it is.
It seems that even if okay. So then there is no.
You can't. If you start out with an arbitrary thing on the left, then no, you don't have a transfer. You don't have a push forward.
You need the twist with the dualizing sheaf in order to get the shadow transfers.
Yeah. Right. Exactly. Think about the case. If you think about the case of a closed immersion, then maybe that's a good example. So, then you just, if here is y and here is x. So here you look at the Gersten complex on y. So let's look at just the generic point. So part of the Gersten complex of y will be, say, Milner-Hurwicz n. Now in this case, d is a negative number because the relative dimension is the codimension. So you have on the k of y, right? You have something like this. And then, but on the, you want to compare the, this is on y, so then it goes with some twists. And then you have this is going to be part of the Gersten complex for x. Sorry, I've run out of room here. Should start out with the Gersten complex for x and plus c. C is the codimension, so c will be my minus d. And eventually you get to the part involving n. This will be codimension c on points on x. And then some funny twist here. And now, but this is where it starts for y. And you just have this one term. Okay, with some funny twists. And you see, in order for the twist here to agree with the twist here, the difference, remember you have this orientation bundle, which if you view this point here, this is the generic point of y, if you view this point y as a codimension c point of x, the orientation bundle is the top wedge of the normal bundle of y in x restricted to its generic point. Whereas if you view it inside of y, the normal bundle is trivial because it's the generic point. So you have a mismatch between the orientation bundles viewed on y and viewed on x, and that's what you have to correct for. So you twist, and we'll say this in more detail later. Okay, since I'm running out of time again, but whatever. Good. Any more questions about that? Okay. So we have this push forward map, and these are both functorial with respect to composition. So once you have a situation like that, if you have a vector bundle, then you can define the Euler class of the vector bundle purely formally by the following definition. This should remind you of, say, a property of the top Chern class of a vector bundle. It's very similar. So we make the following definition. So let's let V to X, this is a P, be a rank N vector bundle on X with 0 section, maybe I'll call it S0. Then the Euler class E of V is defined as follows. So in H0 on X, Milner-Hurwicz 0, this is just Chow 0 tilde of X. Well, this is a sheaf of rings, and so we have the constant section with value the unit in the ring. So I'll call that 1x. And now we can take S0 lower star of 1 on x. So this is the unit. unit section. And then you can pull it back. And so where will this live? Well, when you push forward, you shift the degrees, you increase from 0 to n, and you also have to twist by something. You also, right, you have to know that you can twist by something. But what's the relative dualizing sheaf, the relative omega? It's just the inverse of the determinant of V, right? Because it's just the normal bundle of the 0 section in V. So that already lives on X. So it's possible to do the twisting. And so this thing will live, let me not write it down, but you then pull it back to X and you get something in here in Chow and tilde of X with coefficients in the inverse of the determinant of V. Because, yeah, the omega is the dual of the normal one. Okay, good. Well, because you have to twist in the other direction. Right, yeah. 2 minutes. I thought I had till 15 after. No, but...
It's a 1 hour and 15 minutes discussion, but if you...
Oh, okay. Sorry.
keep going, sorry.
I'll keep going. Okay, good. So,
Child 0 is the line bundle, is it not dependent on the child bundle for child 0?
well, I use the trivial, when I don't put anything, I use the trivial bundle. Okay, so, right? So now if we take X to be smooth, projective, dimension D over K, then we have the tangent bundle of X over K. This is the dual of the differential one forms. Tangent bundle over X. And then we have the Euler class of the tangent bundle of X. This will live in Chow tilde D of X with coefficients. Well, the determinant of this is the inverse of this, so it lives in omega X over K. And this is exactly what you need to take the push forward to Chow 0 tilde of spec K with trivial twist. And this will go to something, well, whatever it is, in here. And then we have following theorem. So we think of this as sort of motivic version, Gauss-Bonnet. That for X smooth and projective over K, the two are equal. That this Euler characteristic with respect to XH is equal to this sort of refined degree of this Euler class of the tangent bundle. Okay, so time's up. So I'll tell you some nice consequences of this result next time. Okay.
For the right hand side, have an equation. I mean, the pi x lower star can only be defined for projective.
Yeah.
But how about the general case? Since the left hand side can be defined for any smooth thing. So
Yeah, right.
That's so.
Well, but then you just have the left-hand side, so you don't have an equality. I don't know what to say. I mean, I can say something, which is that Euler characteristics are supposed to be additive, right? So what would you do if you had a smooth quasi-projective variety and you embed it in something smooth and projective with normal crossing divisor as the complement? You'd remove the components of the divisors one at a time, and then you'd add or subtract the Euler characteristics. So let me just give you a little formula which follows from the left-hand side using the additivity of traces in distinguished triangles. So here's one nice property, that if you have Z inside of X, both smooth let's say that we're in the they're both dualizable. So in characteristic 0, it doesn't matter. And if codimension C, then the Euler characteristic, let me just call this thing the Euler characteristic now, without any decoration, of X is equal to then the complement is also dualizable of X minus Z plus, well, minus 1 to the C times the Euler characteristic of Z, where this is the quadratic form, rank 1 quadratic form with coefficient minus 1. Okay, so, yeah, so you can do that. So it's additive with a twist. Okay.
Willing to say a couple words about how to prove that theorem?
Sure, I
Is
could.
it formal? Is it hard?
Both. To set it all up, it takes me like 40 pages. So yeah, it's long. I don't know if it's hard. So let me just say there are two main ingredients in the idea of the proof. So the first part is we want to represent. So this is pretty straightforward. We want to represent. I mean, this is actually what takes the long time. We want to represent this cohomology theory. So bi-graded cohomology theory. And then possibly put the twist in somehow inside of SH of K. And this follows from Morel's theorem. Morel's theorem says that when you take these sheaves, this is equal to Milner-Hurwicz minus star. Okay? And so what you can do, you can represent this thing. That means these sheaves have nice properties. So they're like if you take the n plus first Milner-Hurwicz sheaf and take its GM loop space, it's the nth one. And that means they fit together to be a homotopy module. So I didn't define that, but more or less it says you can form an Eilenberg-MacLane spectrum with coefficients in these sheaves. You can write it as a P1 spectrum just by in the nth thing. You take the space K, Milner-Hurwicz, n, comma, n. And that'll have the nice P1 loops property to be a infinite spectrum, and that tells you that you get the formula that I guess HA x Milner-Hurwicz B is equal to this Eilenberg-MacLane gadget in degrees A plus B, B of x. And if you want to get the twisted ones, you apply this to the Thom space of the line bundle L. So that's the first part. You represent this, and then you have to construct, well, it has pullback maps, but then you have to construct push-forward maps, appropriate push-forward maps on this theory, and show that they're compatible with the old ones. Compatible with this isomorphism. So that's what takes a while. Okay, so, I mean, it's nothing deep, but it's annoyingly lengthy. Okay, that's the first idea. And then the second idea is you want to look at how you got this dual of x. So that's where the construction of the dual comes in. And more or less, it's always the same. Well, sorry, what's the idea between the usual Gauss-Bonnet theorem? It's just that the dual, this, Spanier-Alexander dual has something to do with how x sits inside of x cross x by the diagonal. And so the second ingredient is you relate the trace of the identity map on x to the diagonal inclusion of x into x cross x, and note that the normal bundle of this diagonal inclusion is the tangent bundle of x, more or less. Okay, so, I mean, that's actually not so difficult. Once you write down what Vojevodsky's construction of this, then you can rewrite this trace of the identity by some standard business to explicitly involve something which looks like taking S0 lower star, S0 upper star. But in this, okay, so this theory is not the same thing as the endomorphisms of the sphere spectrum. But because, so 3, you use the fact that S is T connected, T minus 1 connected, to give a map here to this Eilenberg-MacLane spectrum, which inducing the identity on the pi 0, 0 part, or the pi 0 star part. T, there's a homotopy T structure. So which, yeah, it's basically, it's the obvious thing. The homotopy T structure is you say the positive part are just all the E such that pi A of E star is 0 for A negative, and the negative part, or you just use these homotopy sheaves as graded objects.
So you can think of that as some kind of original.
Yeah, exactly. This is, I mean, in fact, in the paper, I write this as H0 of SK. Yeah, exactly.
So the proof is formal once you have set up the whole context correctly.
Yeah. Okay, well, that's always the case. Thanks. Thanks for giving me an opportunity to say that.
More questions?
Yeah.
It's possible to rewrite the other characteristic as alternating sum and some kind of dimensions of the quantum complex?
I don't think so. I don't know how to do that. It would require some kind of, I don't know. I mean, you have a T structure, but see, this is already the H0. It would require some other kind of T structure. I can't really imagine how to do that. Yeah, Chuck.
If you do this over number fields, do you get some sort of an interesting little number theoretic interpretation?
Yeah, well, yes and no. So now that you mention this, the most interesting for me, the clearest statement is the following. So here's the clearest statement. If you take K inside of C, then this Euler characteristic of X, so let's call sigma, goes, you can take sigma, this is in the Grothendieck-Witt group of K. This goes to sigma star of this thing in the Grothendieck-Witt group of C, which is Z by rank. And as I mentioned, this thing is just equal to the Euler characteristic of the topological space of the C points. But you could also put K inside of R, and then this thing goes to, let me call it tau maybe, tau star of this Euler characteristic living in the Grothendieck-Witt group of R, and then you can take the signature to Z, and then what you get is that the signature of this tau star chi of X is equal to the Euler characteristic of the real points. So it has that nice interpretation. And then, of course, if your X is over, see, I don't know a nice interpretation of what, you get interesting invariants if you're over Q. One of them is the signature, the other is the rank, and that tells you what happens over R and over C. And then over Q, you have these other bits, you have discriminant and, this Hausdorff-Trimester invariant. I don't know what that tells you, except it's an invariant. I have some computations, which we'll see next time, that give examples of things where you get some non-trivial invariants, but more than that, I don't know.
Like say X itself is a projective quadric.
Then I can tell you the answer right away.
You get what you would expect.
Well, what do you expect?
Well, the class of that quadric.
No, you don't.
Not.
Do not. You lose a lot of information. It's an Euler characteristic after all, right? So it's a little disappointing.
With or without real points?
With whatever. You take a quadric Q inside of, So first of all, there's a theorem which I can now take the opportunity to state that, since we're talking about examples, this motivic Gauss-Bonnet theorem tells you if you have a smooth projective variety over K of odd dimension, then its Euler characteristic is always hyperbolic. It's a multiple of the hyperbolic form. And this is a reflection of saying if you take a smooth, compact manifold of dimension congruent to 2 mod 4, then its Euler characteristic is odd, is even. Yeah, because in the middle dimension you have, okay? So it's not just even. I mean, an Euler multiple of the hyperbolic form always has even rank, but it's hyperbolic. And if you take the real points, it says that its Euler characteristic is always 0, which I'm sure is easy to prove by other means. So anyways, take an even dimensional. For that reason, let's take an even dimensional quadric defined by, let's say, a form Q in variables t0 up to t2n plus 1. And let's diagonalize it. You might as well diagonalize it, right? Ti squared. Okay, so this is a quadratic form of even rank. And then so right, so you lose a lot of information. So what's the information that's retained? Then the Euler characteristic of Q is equal to a multiple, I think it's n if I get it right, n times the hyperbolic form plus 2 more terms. You have the form 2 plus minus 2 times the product of the AIs. So in other words, this is just the discriminant of Q. So that's what you get, the answer. So you just recover the rank and the discriminant.
More questions? Okay, keep in mind we have a discussion section at 2:45 this afternoon. There's some more questions after that. Thank you very much.
Yeah, very well.